This is the Module 0 video on collisions and molecular orbitals. This should be a review, but you may not have thought about it in this way before seeing the molecular orbitals that were depicted in the previous video. But when molecules collide, for the most part, they repel each other because of all of the electrons that are occupying bonding orbitals. The only collision that will result in a reaction is between a filled and an unfilled orbital. And this occurs only if the electrons have enough energy to overcome the repulsions from all of the other filled orbitals that may be in the proximity of an empty orbital. So reactions require some energy to occur. And that minimal energy requirement is the activation energy. Now, it's important to remember that in a sample of molecules, there is a distribution of energies. Not all the molecules will be at exactly the same energy. There will be a bell curve, or what in chemistry is known as a Boltzmann distribution of energy levels. And so while the average temperature may be represented by the highest point in this graph, there will be some molecules in this population that will have enough energy to exceed the activation energy. And so in class, I would like to discuss how increasing the temperature from T1 to T2 affects kinetic energy. Turning to the last page of the worksheet, here I will depict a repellent interaction between bromide and chloromethane. This will involve a filled orbital of bromide anion reacting with a filled orbital of chloromethane. In a single occupied molecular orbital, electron density is distributed through all four of the lobes with p symmetry of this HOMO. The lobes of the LUMO are along the axis of the chlorine carbon bond. Now, I will depict bromide and chloromethane in a collision that is attractive. In this collision, the HOMO of the bromide anion is aligned with the geometry of the empty orbital of chloromethane, the LUMO of chloromethane, accepting 2 electrons donated from bromide anion. You might wonder, why did I show the electrons in the lobe of the bromide orbital away from chloromethane? And I'll remind you that the Heisenberg uncertainty principle states that we cannot state where an electron is at any time. I could have just as easily shown the electrons in the blue lobe. It doesn't matter. We'll complete this worksheet and this video So I will ask you to make a claim for which collision is more common between two molecules or ions. You can claim that the repellent interaction is more common between two molecules or ions. Or you may claim that the attractive interaction is more common between two molecules or ions. I'll then ask you to state the evidence for this claim and the reasoning linking claim with evidence. This concludes the Module 0 video on collisions and molecular orbitals.